Hello everyone and welcome to the channel. In this video, we'll be implementing an EEPROM programmer in our Teensy monitor. This video is going to be a bit different from my usual content as it's primarily about software, but I hope I was able to make it interesting. Let me know in the comments either way. I would love to hear your feedback. And without further ado, let's get right to it. Okay, so we've been working on the CPU breakout board for a couple of episodes now, and I'm waiting for it to be produced and shipped to me. In the meantime, I thought I would fix one of the software issues that would really improve the experience of developing code for this computer, and that is adding a EEPROM programmer to the Teensy monitor. When I added the EEPROM here to the circuit, I've connected the write enable pin to a pull-up resistor. So by default, we don't want to enable writes, but we can use the signal from the Teensy to be able to program the EEPROM in circuit and not have to pull it out and put it into the EEPROM programmer. So let's do that now. On the Teensy side, I'm going to need two additional signals, and that's going to be the ROM write enable to be able to start programming, and the manual reset signal. And the reason for that is we want to be able to reset the CPU automatically after programming the EEPROM. So I'm going to add them to the monitor now. There we go. And we need them in the input and outputs. Actually, manual reset is bidirectional because it can be pulled low by other parts of the circuit. And to make sure that's a programming error on the Teensy, it doesn't leave the manual reset pulled high by the chip, which could risk creating a short because the reset can be pulled low by other parts of the circuit. I'm just adding a diode here to make sure that there's no current that can flow from the chip to other parts of the circuit. But if the Teensy brings this line low, then manual reset is going to be brought low as well. So finally, in order to be able to program the EEPROM, we need to be able to pull the CPU off the bus because we want the Teensy to be driving the address and data lines. And so we'll need the bus enable signal as well, which I'll connect to this pin here. And there we go. So when we want to program the EEPROM, we are first going to bring bus enable low. This will disable the buffers on the address and data bus. Then we'll drive the address and data bus from the Teensy with the values that we want to program, and we'll program them by toggling the ROM write enable signal. And at the end, after programming, we can re-enable the address and data bus buffers on the CPU by bringing bus enable high, and we'll send a pulse of manual reset to reset the CPU and restart the program. So now we have to go to the Arduino IDE and write the code necessary to do that. So the format I will be using for the communication between the computer and the Teensy is Intel Hex. And the reason I want to use that is it's pretty easy to work with and it's supported by many assemblers. Unfortunately, Acme doesn't support it, but it will be easy to convert our raw binary to this format. How it works is you have a number of packet types, but we're only going to use two, the data type and the end of file. And the packets are all structured the same. So there's a start code, which is an ASCII colon, a byte count, which can count the number of bytes of data that is in this packet. The maximum packet size is thus 255. Then there's a 16-bit address representing the address of the data that is contained within the packet. So we'll be able to say, for example, the first packet has to start at address 8,000 hexadecimal, and so on for each packet. There is a record type. As I said, we'll only be using 0 and 1, which is the data packets and the end of file. And then there's a data sequence, which is represented as hex digits. So it's not raw binary data, it's hexadecimal digits. And finally, there's a checksum, which is going to be useful so that we can verify that the communication between the Teensy and the computer happened without any byte being lost due to common errors, such as the serial communications being too fast on one side or that kind of thing. Yeah, I think that's going to be a pretty nice way to send data over to the Teensy. And then finally, there's the end of file record, which occurs only once as the last one, and you can use this to know when the transmission is finished. So we have to build a parser for Intel Hex in our Arduino monitor code. Additionally, the monitor code currently assumes that you want to trace what's happening with the computer as soon as you connect to the serial monitor. However, we have now two types of interactions. The first one is programming and the second one is tracing. And so I'll update the monitor code to only start the tracing when a specific character is sent. I guess that's going to be T. And to only start the programming when another specific character is sent, and that's going to be the start byte for the first packet, A colon. Okay, so let's go to the Arduino IDE and program this. So first, let's start by adding interactivity to our monitor. I want the tracing to only start when I first press the T character, and I want it to stop when I do Control C. Okay, so I added some input capabilities to the program, and it will listen to the serial port. And there are two commands at the moment. If I send the letter T, I will start tracing, and if I send the letter Q, I will stop tracing. So now the tracing doesn't happen automatically when I open the terminal, but I have to send the letter T for it to work. Then if I close the serial terminal, of course, if I was tracing, I want to stop tracing so that the CPU resumes normal operation. So let me show you a demo. So if I open the serial monitor, you can see that nothing is happening. But if I press the letter T and send, you can see that it starts tracing. And if I reset the CPU, you can see that it traces what's happening on the bus. Now, if I send the letter Q, you'll see that it stopped tracing, and the LED on the Teensy also is turned off. And that signifies that the CPU is resuming normal operation. Now I can start tracing again. You can see the LED is lit up. The frequency is quite slow because that's the tracing frequency. And now if I close the serial monitor, you'll see that it resumes normal operation. All right, so that was the first step towards adding more commands than just tracing on the Teensy. I've written some new code to handle the Intel Hex format. So you can see in the loop here, I've added a case where if the command starts with a colon, which is the start of an Intel Hex file, we want to begin programming. And so we go to handle programming. One other thing that I've added is we have to skip over spaces and carriage returns and line feeds, because if we send an Intel Hex file, typically the records will be separated by spaces and new lines. And by default, the Arduino serial monitor sends a line feed, so it's good to ignore those. So if we look at the handle programming function, you can see that it loops until it has reached the end of file packet, and it reads packets one by one. The first thing it does is it reads the various metadata, so the count, the high byte of the address, the low byte of the address, and the type. And you can see that these are the 4 first bytes of every data packet. And it also starts computing the checksum, which contains all those metadata elements. And then it does something depending on the type of the packet. Of course, if we don't support the packets, there's an error, so we have to print an error and break. At the moment, I'm supporting packet type 0 and 1, and that's the data packet and the end of file packet. And once it has read the packet, it will consume everything before the start of a new packet. That is the line returns or the spaces that you could have in a file that has packets on each line. So I've written a couple of helper functions to do all of this. The first one is blocking serial reads. So we want to read a byte and we want to wait until data is available to return the byte. The second one is read hex as byte, and this one does two blocking reads from the serial port, and it interprets the result as a hexadecimal representation of a byte. And that's because the format of Intel Hex is to represent bytes in textual form as a hexadecimal with 2 characters. So it's a text format, not a binary format. And I've also had to write a simple helper to convert textual representation of a byte with an ASCII digit to the corresponding number. The end of file packet is pretty simple. If the type is 1, then we know we are reading an end of file packet. We have to consume the checksum bytes from the serial data to consume the whole packet. And then afterwards, we can set that we have reached the end of file, and we can we said that we have reached the end of file, and then this is not going to do blocking reads, and it's going to return and terminate the programming mode. And then the more interesting case is packet type 0, and that's a data packet. So we grab all the data and we want to verify the checksum before doing anything with the data. So we have to store the data in a buffer, and the maximum size of the packet is 256 bytes. We read data up until the count is reached. That was the metadata element in the packet header. And for each byte that we read, we also add it to the receive checksum, which means that after all the data has been read, we can read the checksum byte. And if we add the checksum that we computed to the checksum byte, we should always find 0. If we don't, then we had some problem receiving the data and we can ignore the packet. And then we have to do something with the data. That's going to be EEPROM programming. But for now, I'm just printing every byte of data I receive as hexadecimal. And that's another helper function, which prints through the serial port the hexadecimal representation of a byte, but with a leading 0. Okay, so let me upload this and test it. I'm going to use the packets that we can find on Wikipedia, because I'm going to assume they're valid. So let's take this one, for example, and send it. And we can see that the Teensy responds with the data that was in the packet, which is here. If I take this one and send it, you can see that we also have the data that was in the packet. So now if I change some byte to trigger the checksum error, you can see that it says invalid checksum and it didn't process the data. If I send a packet that we don't support, for example, this one, packet type number 2, it says that we received an unsupported record type, but I can still send valid packets. And at the end, I have to send the end of file. Nothing is printed, but now I can do other commands. Again, I'm out of programming mode. I can start tracing, etc. And I can go back to programming mode just by sending a packet with a colon. If I just send an end of file packet, nothing happens, of course, because it's an empty file, but I can send a data packet again, and I have to terminate it with an end of file packet. All right, so I think this works well. Now we have to talk about what we're actually going to do with the data. And for that, we'll look at the programming algorithm of the EEPROM in the datasheet. Let's look at the datasheet of the AT28C256 EEPROM, which is the one I'm using in my circuit, and see how the programming algorithm works. So there are two writing modes that you can use, the byte write and the page write. The latter is faster, but it's also more complex, so we'll start by implementing the byte write. So the way it works is a low pulse on the write enable input with the chip selected and the output disabled initiates a write cycle. So this write cycle is going to last a long time, and we'll have to implement some polling to verify that the write cycle is finished before writing another byte. So the address of the byte is latched on the falling edge of write enable, and the data is latched on the first rising edge of write enable. How do we know when the chip has finished writing a byte internally? Well, there are two things you can do. We can either use data polling or the toggle bit. For data polling, it means that if you attempt to read the last byte that you wrote, you will get the complement of the written data on the IO7 pin. And once the write cycle has been completed, the data is valid on all the outputs, and you can begin a new cycle. For the toggle bit, so it's another method for determining the end of a write cycle, the IO6 pin will toggle between 1 and 0 for each successive attempt to read data from the device. Once the write is completed, IO6 will stop toggling and you will read the valid data. So we can implement either of them. I think I'll go with data polling, but it doesn't really matter. If we look at the timings of the write, we're not going to use the chip enable control, we're going to use the write enable control because that's the pin that the Teensy is controlling. So first of all, we have to ensure that the CPU is not driving the bus when this is happening, because we need the Teensy to be able to drive the address on the bus and the data on the bus as well. So we'll have to tri-state the CPU buffers before we start. Doing that is going to disable the output enable of the ROM because it's connected to the read signal, which is tri-stated when bus enable is brought low. Then the Teensy needs to write the address on the address bus. And this is going to go through the address decoding circuit and make the chip enable go low after some delay. And whenever those three conditions are met, the outputs being disabled, the address being valid, and the chip enable being low, you can start the write pulse. And the time that you have to wait is a minimum of 0 nanoseconds, so you can do it immediately. We're going to have to add a delay because we don't control the chip enable pin. That has to go through the decoding logic, and so we'll have to wait a bit before starting the write enable pulse. Once we have brought write enable low, we can start outputting the data on the data bus. And we have to output it at least TDS, so the data setup time is 50 nanoseconds before we can bring write enable high again. And this is going to latch the data. After that, we have to hold the data for 0 nanoseconds, which is great. We can start changing it immediately. Same thing for the address. The chip enable hold time is 0, so we can start another cycle. And then we also have to make sure that the write pulse is low for at least 100 nanoseconds. And then before starting a new write cycle, we have to ensure that we also have to wait 100 nanoseconds. Okay, so let's go into the Teensy IDE and start implementing this. So we'll start by defining our pin. So the master reset we have on pin 5. Bus enable is on pin 4. And the ROM write enable is on pin 7. So when we start programming the computer, we want to set up our control signals. So the first thing we want to do is we want to put the CPU into reset because we want it stopped during the programming operation. Second thing we want to do is we want to disable the CPU buffer. So we want to put bus enable low. And then when we are done programming, so when we receive the end of file on the Intel Hex format, we want to bring bus enable high again and finish resetting the computer. And I'm going to add some delay before the CPU is reset so that we are sure that the CPU buffers are indeed enabled. And same thing over here. After bringing bus enable low, I'll just add a delay so that we're sure that the buffers and all the glue logic is effectively disabled. Of course, we have to set up our pin. So bus enable by default, we want set to 1. Let's try this out. Okay, so when I send the first byte, we should put the CPU into reset and bring bus enable low. So let's see if that happens. And yeah, as you can see, the reset LED in red has lit up, the bus enable LED has lit up as well, and now the address bus is being pulled up because nothing else is driving it. Okay, so I extracted two new functions, start programming and end programming that contain what happens to the pins when we start programming and when we finish programming. I've also started on implementing the program byte at address function. When we receive an Intel Hex packet, the address in the packet is going to be a base address offset. Typically, it's going to start at the base address of the ROM, and it's going to increment with each successive packet. And then within each packet, each successive byte of data is programmed at an incrementing address. So we take the base address offset, we add the count that we're at, and at this address we program what's in the buffer. And then at the moment, this is only a shell, and it's just printing out the address and the data. So let's try it out. So if I take my usual data packet from Wikipedia, we can see that it's going to program at address 30, the bytes 02, at address 31, the byte 33, and at address 32, the byte 7a. And we can try the other example. And this one starts at base address 10, and in increments until address 1a. So we'll have to make sure that when we build the binary file for our ROM, we start the base address at 8000, because that's the base address of the ROM, and then increment from there. Okay, so let's start implementing the actual programming now. All right, I made some progress implementing the programming algorithm. First thing I did is we have to set the address and data bus as outputs. So I'm using port registers and DDR registers here, which I've defined here at the top. And I've also removed the pin definitions that we had, and I'm using the same registers in the setup here to set them up as input. So now that when we start programming, we set them at output, we can drive values onto them. And when we end the programming session, we have to remember to set them back to inputs before enabling bus enable. So now that we can drive values onto them, we can set the address on the address bus when programming, and we can also set the data on the address bus. And I have here, let me uncomment these. And I have here the write enable pulse, which we start here. Then we set the data on the data bus, and we wait for 2 knobs to satisfy T data setup, which is 50 nanoseconds, and T write pulse, which is 100 nanoseconds. And then we stop the write pulse, and this is what's going to latch the data in the EEPROM. And then we wait again because there's a requirement on the total write pulse size as well. Okay, so let me comment the write enable manipulation because I don't want to write to the ROM just yet, and upload this program. So I have crafted a spatial packet where the data has an offset of 8000. That's the base address of our ROM. And there's a signal byte, which is CB, and that's the wait instruction. And so if we're able to successfully program at 8000 CB, we'll see the CPU go into the wait state immediately after reset. Then we have the end of file record. So if I copy the first one and execute it, you can see that it goes into programming mode. It drives 8000 onto the address bus, and then this is CB over here. And then if I send the end of file packet, you can see that the CPU resumes operation. So now the only thing missing is actually programming the byte. So let me uncomment these and re-upload the program. And if we send both those packets at the same time, we should program CB into the first instruction of the program, and it should wait immediately. So let me do that now. So it didn't work. Okay, so the reason that what we did just didn't work is because the ROM has write protect enabled. And you can see that in our makefile. When I do make EEPROM, I execute minipro with those arguments. And I need to add the no write protect argument so that write protect is disabled. And I can program the EEPROM with my Teensy. So let me grab the programmer again and reprogram this without enabling write protect. There we go. So as you can see, it disabled the write protection and it didn't enable it again. So we should now be able to try our test program. So as a reminder, this will replace the first byte in the EEPROM with the wait instruction, and so the CPU should immediately go into the wait state after it's reset by the Teensy. And yeah, that worked. This is the wait LED, and the CPU is not doing anything, so it's in the wait state. Awesome. Now, the reason that worked properly is because we only wrote 1 byte, and the ROM had time to register the write before the CPU got reset, because the reset pulse is at least 150 milliseconds, and I'm assuming the time for the ROM to register the write is less than that. But in order to write more bytes than just 1, we have to implement polling. For polling, we have to repeatedly read the data bit number 7, and this will be the complement of the written data until the write has finished. So let's implement that. All right, I successfully implemented data polling, so I'm going to walk you through it. After we finish writing the contents of a Intel Hex record, we poll for the end of the write operation using the last byte that we have written. And what the data polling function does is it will repeatedly read the data present at the address until the result is equal to the data that we want. So in order to do that, I had to connect the read pulse to the Teensy, because we need to control the read pulse from the Teensy to be able to read from the EEPROM. So I'm just going to make this connection in KiCad. I've added it to pin number 3. And there we go. And so on the EEPROM side, read is connected to the output enable, and that's the pin we want to control from the Teensy. So in order to read from the EEPROM the last byte that we have written, we need to set the address pins to the right address. We want to set the data direction register for the data port to input. And we want to set read to an output, and we start by setting it to 1, so it's disabled. The signal is active low. And then until we read the correct data, we want to repeatedly read from this location. So we start a read pulse by writing 0 to read. We wait for 3 nops in order to satisfy the data access time of 150 nanoseconds on my EEPROM. Then we get the value of the data, and we stop the pulse. And after that, it takes some time for the ROM to be disabled, so we wait for a bit. Then I have some logging, and if what we read is different from the data that we want, then we continue repeatedly this loop. And as you can see, on my last attempt, it took 46 iterations of the loop before the read data was equal to the data. So that works. So we are now able to program more bytes than just the 1. And specifically, we are able to implement the page write mode, where you do exactly the same thing as a byte write, but as long as you write fast enough, you can write 64 bytes of data before you have to do a polling operation. So each successive byte must be written within 150 microseconds of the previous byte. Otherwise, the write operation finishes. And without Teensy, I think we can meet this pretty easily. What we'll do is we'll make our Intel Hex packets 64 bytes long. This way, this code already works. We're going to write 64 bytes, and then we'll do a data polling operation. I'm just going to add a check that the count of bytes is less than 64, because we can't handle more than that. And then we can reduce the size of our buffer to 64 bytes as well, because we're never going to exceed this. All right, and so this should work as is. We just have to send 64 byte packets to the Teensy, to use page write mode. So in order to test the page write mode, I've created a special packet, which is incrementing bytes from 0 to 63. The length is 64 and it starts at address 8000. So if this programming operation succeeds, we should be able to read this using the MiniPro and verify that the ROM contents have been overwritten to this. So let's try it. So I'm going to send this to the Teensy. Okay. Now let's pull the ROM and read it with MiniPro. And yeah, it works. You can see here the first bytes of the ROM are actually incrementing bytes from 0 to 63. Awesome. Let's try sending this a couple times so we program more of the ROM. We just have to increment the base address. So let's try sending this to the Teensy. Of course, we have to change the checksums. Let's try again. So it did something. Let's see if the programming worked. So we can read it again. As you can see, I was able to program my EEPROM for my 6 Intel Hex records. Now, the next step, of course, is to be able to convert the binary file that Acme produces to the Intel Hex format, and that's what I'm going to do next. Okay, so I have found the Intel Hex library in Python that helps with manipulating Intel Hex files and creating a script to convert our main binary to Intel Hex is really easy using this library. You just have to import it, load the binary with our 8000 offset, and then export it to a file in hex format with 64 bytes per packet. And this is the way that you use it. And the output that I get is a file that contains 64 byte packets containing the binary data of my EEPROM. You can see here at the end, we can verify that we indeed have our reset vector set properly and that it goes to 8000, which is the start of our program here. So this is the data that we should send to the Teensy to program the EEPROM. So let me try this now. And it seems that the polling is hanging. So let me increase the delay here. And try again. And it looks like this is not enough. Let's try 200. And yeah, this works. Okay, so I've integrated the whole chain into my makefile now. So when I compile my program, I run the bin2hex Python script that generates the main.hex file. And then when I run make EEPROM, instead of calling out to MiniPro, it will echo the main.hex file to the Teensy directly through the shell. So I don't even have to run the Arduino IDE for this. So let's test this. So this display is now showing hello world. Let's change this to hello YouTube. And we can compile and make the EEPROM. And you can see now it's programming. And it will reset and print hello YouTube. That's awesome. Now let's go back to hello world. Make and make EEPROM. Awesome. This is great. This is going to save me so much time. Now, there are a few improvements that we can make to this. The first thing is we need to verify the data has been written correctly. The second one is we may want to restore the write protection on the EEPROM. That should be pretty easy to do. And then finally, in order to protect against programmer errors, I want the computer to be able to verify the validity of its EEPROM without any involvement from the Arduino code. And that's going to be the subject of a future video. So I hope you enjoyed this one. I know it's been a bit different than my usual content. This one has been pretty software oriented, but it had to be done. It's going to help me work so much faster when writing code for the computer. And I hope it was pretty interesting to you as well. So in the next video, hopefully we'll have received the breakout board PCB. So we'll do the assembly for that. In the meantime, if you have any questions or feedback, let me know in the comments. And I hope to see you in the next one. Goodbye.